the equation here I'm writing down is the second derivative of x plus f equal to 0, right? It's actually an interesting special case for a equation we have discussed before. The equation we discussed before is actually the advection diffusion equation with a time derivative, right, plus a times du dx is equal to a kappa times second derivative of u. And when we discussed the advection diffusion equation, we actually didn't add an additional f over here. But in a little bit more general sense, actually, if you solve this with finite difference or finite volume, it's almost trivial to add another known function f to the right-hand side, right? I trust you can figure out how to do that. If you do it with finite difference, it's just at every grid point, you can just add the value of f on that grid point. All right. Oh yes, the question from Chris is this still for the case when f equal to 1? The answer is yes, because we never changed our b. So our b, it's still computed assuming f is equal to 1. Actually, in this lecture, we are going to be discussing later on how do we generalize to other cases when f is not equal to 1. All right. Yeah, thanks for the question. Okay, so now let's consider the case a equal to 0. So there is no movement, no bulk movement of the solution. Kappa equal to 1, so that essentially the diffusion dominates. And t goes to infinity. All right. So what happens when t goes to infinity? Remember, we have been solving the equations, right? As t goes to infinity, everything diffuses away, right? So the solution u goes to steady state as time advances to infinity, no matter what initial condition we have. So really, this equation is the limiting case of an advection diffusion equation with an additional what we call source term. And the particular case with no advection is a good model for the diffusion of heat in a solid body. This equation is really solving for the case when you have a distributed heat source. So you can interpret the F as a distributed heat source. Okay, and the kappa is going to be the heat diffusion coefficient. So it is essentially asking if you have a distributed heat source and let the piece, the solid metal piece, become equilibrium, right, as t goes to infinity, what is going to be the temperature distribution on the solid piece? So that's what it means by the solution to this equation. And now let's get to the boundary conditions. If I set the value of u 0 equal to, let's say, T0, that essentially means I know the temperature on the left side of the piece, right? I basically have the left side of the piece in contact with essentially something like something of a constant temperature, right? Something that has a much higher rate of heat conductance, so that you know the temperature on the left side. That's why I'm saying this is a special case. You can have different boundary conditions. For example, if instead of specifying a temperature on the left side, what if I specify a heat flux? What if I specify like a heat flux, which is how much heat I put into the left boundary per unit amount of time? What kind of boundary condition would that correspond to? Well, that's actually an interesting question, right? because if you know the amount of heat, it actually tells you that because we know the equation of heat conductivity, the amount of heat that is conducted is proportional to the temperature gradient. So setting a heat flux Q, which is heat flux, is essentially setting Q equal to kappa, which is equal to 1 here, times du dx at x equal to 0. So that's actually another type of boundary condition I can specify. So this is the setting the solution is called sometimes called the Dirichlet boundary condition, and the setting a derivative of flux of heat is sometimes called the Neumann boundary condition. Okay, so let's spend a little bit time discussing what happens if I set a Neumann boundary condition, a derivative, fix a derivative instead of fixing the value. And it turns out it's actually a very interesting problem to consider, because if you set a derivative on the right-hand side or on the left-hand side, you actually, it does interesting things to the number of unknowns you have in your solution. Why is that the case?